Hello, my name is Carlos Morales. I run the AI group here at Ambiq, and today we're going to talk about one of our new products, our new software products called neuralSPOT. Today we'll focus on what neuralSPOT is, and we'll actually go through a short demo of running your first application using neuralSPOT. Okay, so what is neuralSPOT? I think the genesis for neuralSPOT was about a year ago when I joined Ambiq, and I'm trying to get the first model running. And I realized that Ambiq has an amazing software library. It's called Ambiq Suite SDK, but it's a library that's designed for embedded engineers. And luckily I had an embedded background, and so I was able to kind of integrate all of Ambiq Suite's features into my first model. But I realized that there was a learning curve involved. Most AI developers are not going to go through that, or don't really want to go through that learning curve. They want to focus on their neural architecture and getting their accuracy up, not how do I make the microphone work. And so we started putting together this concept of neuralSPOT, which is it's an SDK on top of an SDK. It's a software development kit and toolkit that's built on top of Ambiq Suite's already very, very comprehensive SDK. It's open source, so it's licensed under BSD3. Everything that you have there, you're free to use, commercial, non-commercial. It's developer focused. As I said, the concept was kind of refined as we developed our AI models. So it's been evolving with us as we learn things, and it will continue to evolve. And then finally, it's an SDK and a toolkit. So a software development kit, meaning it has all the libraries you need to integrate into an Apollo 4 development platform. But we also have some development tools. So that's what the toolkit means. And what we mean here is ways for you to connect your development platform to a laptop so that the Python world, which is where AI development lives, at least in the training space, and the deployment world can communicate with a little less friction. And so once we've wrapped everything in these things, you can start doing really cool things. Like I optimized once, and now all that work I did to optimize, say, power performance around how you read an audio sample, you just use our library and you get that. Now you may have to tweak it for your hardware if you have a different microphone, for example, but the basis is there. So it's on GitHub, and we'll send the links out. I mean, the links are actually at the end of the presentation. I think it's important to note that this is reference software. It's just like any other open source project. So really, there's no support guarantees. You use it as is. But of course, we're proud of our code. So use GitHub's issues mechanism, and we'll do our best to resolve those issues. And we're always looking for external collaborators. So if you get excited as you're using this and you want to be part of the development team, or you want to submit some fixes or code, we use normal open source kind of mechanisms for that. So I kind of alluded to this, but what is the problem that we're trying to solve with neuralSPOT? And so the overall goal is to get that model running. You have a model, you downloaded or you have a TensorFlow Lite model running, you want to get it on your EVB as quickly as possible. And so that's what we want to do with neuralSPOT. One of our a good test of that was that earlier this week we received a customer asked us to try running a model on Apollo 4 for us, the proxy model. They don't want to share their model, so they share a proxy for that model. And it took me half an hour to get it to compile, and then another half an hour to measure what they wanted us to measure. So that's a good indication that all the hooks are there to get a TensorFlow Lite model running on an EVB. So that's it. That's my overarching goal. Get it running in less than a day. And not worry about all the other stuff, not worry about how you compile TensorFlow and how you link it in and how do you hook up sensors and so on. And then the other problem is once you have a model running, there are friction points. How do you get data maybe your sensor isn't ready. How do you get data to and from your model? How do you compare your laptop's behavior um, to your actual deployed model behavior? And so that's the problem number two. Let's dig into each one of those a little bit deeper. So how we solve neuralSPOT, how neuralSPOT solves problem number one is with a series of libraries and examples. So if you look at how you actually deploy AI on a endpoint device, it's not just the AI. AI is that middle part there, is the inference. You have to, sense data. You're actually usually acting on sensed data. You have to kind of process that. So you extract features, you may compute a spectrogram. You run the inference, and then you have to do a bunch of stuff with it. You have to, in our case, demos, right? So we print out results. But say you're doing a denoising algorithm, you have to take the output of that inference, which is an anti-noise mask, apply it to audio, and then send that audio somewhere else. So all that stuff is not AI. Sensing, doing DSP, that's not necessarily what your AI scientist, data scientist wants to focus on. And so that's what neuralSPOT facilitates. And then at every one of those stages, we make sure and we continuously optimize. So we make sure that it's as power efficient and compute efficient as possible. That's a never-ending process. So if you look at neuralSPOT's power efficiencies, it's going to get continuously better over time. So that's problem number one. That's how neuralSPOT addresses it. Problem number two is, how do you connect your laptop development environment to your EVB? And this, I'll tell you what my first encounter with this problem was. I was computing a Mel frequency spectrogram on my laptop, and that's using Python, and it's using infinite, floating point accuracy. And it's, the numerics are different, and then it's on an x86, which even the fundamental numerics are different. And then I computed what I thought was the same spectrogram on the EVB, and the numbers were almost exactly right, but they weren't. There were some differences. And those differences were enough to cause my model to lose accuracy. So debugging that was very painful. You would print something out on your laptop, you would copy it into a header file, you would compile that header file, and then you would see why the differences were happening. So we set out as a team to solve that problem. And the solution we came up with was implementing a remote procedure call mechanism. And for people who are familiar with the cloud environment, remote procedure calls are how the cloud works, right? There's all this very distributed compute happening. And if you had to worry about where the compute was happening when you wrote the code, you would go crazy because there's millions and millions of routines running. It's famous, right? A Google search results in something like 20,000 remote procedure calls. So we implemented a very small version of that based on an open source library called embedded RPC. And what it lets you do is it lets you call the function on your EVB that you implemented in C firmware. You can call it from your laptop as if it were running locally on your laptop. So say that you have your model running on your EVB and you want to invoke that model on your laptop to measure its accuracy on your data set. Well, this is how you would do it. When you develop your code on that laptop, you could pretend that the EVB was actually part of the laptop. And you could do the other direction too. So say that you're developing your model and you're having problems like I had where the Mel spectrogram wasn't matching. And you want to say, okay, I'm gonna debug that later. I just want to make sure that my model is accurate for the right feature that I extracted. So you could actually implement your model on your EVB, but when it's time to compute your spectrogram, you call a function that's actually living on your laptop. And we use this internally. We use this for a lot of things. We use it for visualization, data, like visualize spectrogram. EVBs don't necessarily have good displays. They have a little tiny kind of watch-like display. So We use it for feeding data sets to, we use it for a lot of stuff, but for collecting data from sensors and so on. And it's based on something called ERPC. So we've defined one interface, but ERPC lets you define any custom interface that you want. So we have instructions in neuralSPOT on how to define your own interfaces. So how does that integrate with the AI development lifecycle, right? This is kind of the generalization of how AI is developed. In reality, there's a lot more loops and feedback and correction loops and all this stuff. But this is basically those arrows capture how you do things, right? You go from move, you kind of look at what data is available. You start thinking about what kind of neural architectures best operate on that data. And then you start refining it. Once you've done that, you've tried a few architectures, you start refining those architectures. You pick one that's the best, and then you start, maybe you train on the full data set, you start increasing your accuracy, then you compress it, and then you deploy it to your model, to your EVP. So neuralSPOT tools help with a lot of those different steps, right? And I've tried to kind of capture here using the diagram, the bottom of the diagram, where neuralSPOT helps. Those remote procedure calls help with data capture and labeling. The model zoo, which is it's not part of neuralSPOT, but it's something that's based on neuralSPOT. So I'll briefly talk about that later in this presentation. Uses those facilities as well. And then once you get all the way to the deploy, of course, now you're using neuralSPOT and Ambiq Suite underneath it. Okay, and kind of the block diagram here, just so we understand all the different components. Those tools sit at the top. They're written in Python on the laptop side, and of course C on the EVB side. There is a big pile of examples. So some examples are built into neuralSPOT, and we'll talk about those in a minute. But there's also, of course, our model zoo, which is those are great. Those are professional quality, high accuracy, end-to-end models. And so those are also those use neuralSPOT, so you can use those as examples on how to use neuralSPOT. Then there's the SDK itself, and here I just listed a few of the like the libraries that we have. We have power management libraries, we have memory management libraries, we have a whole kind of audio library and drivers. We have several, like we have I2C, and then we have some drivers that sit on I2C for things like accelerometers and ECG, sensors. And those things all, for the most part, interact directly with Ambiq Suite and then through Ambiq Suite with the hardware. Now, there are some arrows that kind of flow around Ambiq Suite. For example, if you call TensorFlow, TensorFlow will talk directly to the CPU using CMSys. And we also have CMSys, where you talk directly to the CPU using CMSys. But all Ambiq peripherals are mediated by Ambiq Suite. Let's dig a little bit deeper into some of these things. So RPC over EVB. Something I didn't mention is that when you do that remote procedure call, we're using the second USB port on your EVB. And I'll show you a picture of how that looks in a minute. I've already, I think, captured most of that. The next thing, the generic data RPC, is the one interface that we include with neuralSPOT. And it's basically a way to send blobs of data back and forth between your laptop and your EVB. And it's bidirectional. Your laptop can be a server or a client in the same way their EVB can be a server or a client. That blob of data is wrapped in some metadata. So you can give instructions using this interface on how to use that data. Hey, this is a WAV file. Please use it as a WAV file, right? Or you can use this as a MPU accelerometer data file. So we have kind of families of libraries. At the top, we have the AI libraries. And these are not so much specific to Apollo 4. They don't necessarily use our peripherals. They use the Cortex processor. And then they use external libraries, so CMSIS, and so on. And most of this stuff is calculating features. So TensorFlow Lite integration plus a number of feature extraction libraries that use CMSIS DSP to efficiently calculate things like spectrograms and so on. Then we wrap all the sensors in easy-to-use mechanisms. So for example, for audio, you say, hey, please, I want this sample rate, this sample size, I want this kind of mode, and then we do all the mechanics of configuring our audio peripheral to expose that as just, here's some PCM data for you to operate on. Since we do that wrapping, we can do fancier things like calculate MFCC, a MEL spectrogram, as the audio samples come in. And we also do, making that stuff power efficient and using it in a way that uses the least microjoules per sample. There's a lot of little settings that experts know, and so what we try to do is capture those expert settings into that driver. Beyond that, the Apollo 4 is a complex device with a lot of peripherals, settings, memory configuration that all impact performance. So we have a library that lets you do that in a single function call. So we've done the work, for example, of knowing what to turn on and off if all you're going to do is audio inference. So it's one call. You go set power mode, low power audio, or debug audio if you want to enable debug interfaces and so on. We have a bunch of little tools that help you monitor things. So these aren't necessarily things that will go into your final product, but say you want to know how your cache is behaving. So we'll print out your cache information for you. Or say you want to mark a region in your power monitor and say, hey, this is the inference region. I want to measure power during that region. We have little libraries that help you do that. And basically things that we've written for ourselves, and we're like, oh, that is useful. And we just package them and make them available. And then finally, there are a bunch of utilities that help you do common things like reading a EVB button, turning on an LED, malloc. So usually to have so taking a step back, in the real-time OS world, dynamic memory is bad. Right? We try to statically allocate everything. Because when you allocate memory, it's not always deterministic. So if you look at neuralSPOT, you won't find a malloc anywhere in production path, except RPC. RPC is a C++ based library. So what we did was you only use it for debug. Of course, RPC is not production, and so we've kind of wrapped C++'s hidden mallocs, like when you create and destroy things. And we're using our own mallocs based on FreeRTOS's Heap4, which is a good compromise between real-time and functionality. But so that just gives you an idea of the kind of things that we did, like setting up a timer to interrupt you every 20 milliseconds. There's a lot of registers that you have to read and write, right? And there are some Ambiq suite helpers that will help you do that, but you still have to instantiate interrupt handler and there's a lot of little steps that you have to know how to do that. So in neuralSPOT, you just say start timer and this is my callback. So every 20 milliseconds, call this timer. Just a bunch of little things like that. And we do pull in external components. Of course, Ambiq suite is the biggest one. We support 4.1.0 and 4.3.0 today. As Ambiq suite releases, we incorporate those into neuralSPOT. We also support TensorFlow. So the libraries are pre-compiled. You don't have to worry about compiling a static library. And we have multiple versions of that. So if you're trying to debug, where you turn on all the prints in TensorFlow, and there are a lot of prints, you would link in the debug library. If you're looking for performance, you integrate the release library. We have ERPC, where we stripped everything out that's not needed. So the stuff that's in neuralSPOT is just what you need to communicate over USB. And then we have, of course, CMSIS, neural network, and DSP functionality. And then finally, I think as developers, remember this is developer focused, we all start from examples. And so we've included a bunch of examples in neuralSPOT. The first one you want to look at is the basic TF stub, right? The basic TensorFlow Lite micro example. It's we use an open source keyword spotting model that's in TF Lite. We instantiate it, we deploy it to memory, but we also use neuralSPOT to collect audio, to do prints, to turn on deep sleep mode, all these things that you would do in a real application. We wrap that TensorFlow model in there. So if you want to understand like an end-to-end flow, including RPC, I would start there. We have a number of RPC examples that show you how to collect data from accelerometers and so forth. And so those examples include both the Python side and the EVB side. And those, you know, that example code is used by sensor capture for the accelerometer and the audio. And then we have a couple of external integrations. So what we wanted to show was how easy it was to take a third party's model and then kind of layer it on top of neuralSPOT. So there's a company called Edge Impulse, which makes it very easy. It's this low code kind of environment where you upload your data, you let its AutoML kind of pick out the right architectures for you, you guide it, you let it train, and then you click download. And what you download is a C file, well, a blob of C files. It's a whole library. So in neuralSPOT, we have a projects directory where we port that generic C++ model to neuralSPOT and we execute it. Now they do use mallocs, so I'm not a fan, but I'm not a fan of the mallocs. I'm a big fan of Edge Impulse. All right. So without further ado, we're going to get into the demo. So before I jump over to my terminal screen, what we're going to do is actually go from scratch. We're going to download the neuralSPOT repo in its entirety. I'm going to compile it. I'm going to deploy it to this EVB that you see here, and then I'm going to show you what the model does. I'm using a microphone. You don't have to use this microphone, but a powered microphone works well with our analog input. I haven't had good, unless it's a very sensitive microphone, a non-powered microphone doesn't work. I just happen to have this one lying around. And you'll notice that I use both of the USB ports. So for this demo, we're not going to do RPC, but when you enable RPC, the data for that remote procedure call function is going over the second USB port. The first one is used for JLang, for flashing, and for printing and stuff like that. All right. Clean. Now, clear. Can you guys see? I assume you guys can see this. All right. So actually already cloned neuralSPOT. It takes 45 seconds, so I'm just gonna not download it. But if you want to download it, it's a simple matter of typing this in. So git clone, and this comes from our neuralSPOT Ambiq AI website. You do a make. Make is gonna go really fast. There's not a lot of code that you have to make when you build neuralSPOT. A lot of it is already pre-compiled static libraries. But you'll notice that after it compiles all its internal libraries, it will produce about, we're looking down here, really four targets. An MPU data collection example, an RPC client, an IPC server example, and then the basic TF stub. And each one of those is a binary that you could deploy to an EVB. the way you deploy is you say make deploy. That uses JLink to flash. If you want to, and when I do that without any further qualification, without any further settings, it will deploy basic TF stuff, which is what we want today. But if we wanted to do something different, I would say target equal whatever, like one of the other things. So we'll just do make deploy. There we go. And now it's flashed. And to hook up the again, the JLink debug interface, SWO interface, you do a make view. So now we're connected, everything's ready. I'm gonna hit the reset button on the EVB. And this is what this example does, is basically it uses the Google Speech dataset, which is an open source dataset. And it listens for 1 second, and whatever I say during that 1 second, it'll try to guess, right? So I have to press a button over here to do that. It didn't say anything there, so it says unknown. That's no voice. Yes. So let's look at what happened there. It heard something, it classified it, and with 45% certainty, it decided that it was a yes. That's not a very high certainty. And 39% no. Now, this is a funny story. None of these data models, understand my yes. For some reason, my yes is very different from other yeses. Could be where I learned my English. All right, let's do no. 70% certain, better. Essentially, just a little microphone. Up, down, left, right. Okay, so that's basically what it does. I ask you to visit everything and leave us GitHub stars, right? So these are all the resources that are available today. The on-ramp is ambiq.ai, which is live. It includes some introductory articles, links to our models and so on. We have a GitHub page with 4 or 5 open repos, including neuralSPOT, NNSP, which is our neural network speech processing model. And those are actually 3 models. It's a voice activity detection model, a keyword spotter, and a speech to intent model. And while I'm here, so our model zoos are not like the examples that you just saw, right? The examples you just saw are pre-compiled. All the weights are there. They're really just examples of how to deploy a model using neuralSPOT. NNSP and the ECG arrhythmia classifier are completely different beasts. These are end-to-end, kitchen sink, everything included models. So this is what a data scientist would actually start from, right? If you want to look at how to do keyword spotting and modify it for your own purposes, you would go to the NNSP repo. And it has training scripts, it has data preparation scripts, and then deployment scripts. So you would take that, you would train it using your own data because a lot, AI is all kind of data regulated these days. So you can, like, we use public domain data sets that are usually non-commercial. So meaning that you can use them to research and to develop, but you can't really use them to deploy a commercial product. So NNSP shows you how to do that, but you would have to, like, your customers have to provide their own data. ECG arrhythmia classifier is very similar. It uses an ECG sensor, a single lead ECG sensor. You hook it up to your heart. You put your button out, your finger on it, and then hopefully it's boring and it says you're normal. But it'll look for afibrillation in there, arrhythmias. And again, these things are just where they are now. They're going to continue to be extended. We're going to add more features or classifications to it and so on. We realize that this is a lot. So everything here is documented to the hilt. There's top level documentation on the neuralSPOT GitHub page and on Ambiq AI, of course. The model zoos are highly documented as well, and some of them include Jupyter notebooks that help you kind of step through these things. The code itself is documented using Doxygen, which is kind of inline comments and automatic documentation page. And then videos like this one usually get posted on our YouTube channel.